Good morning, everybody. It's really an honor to be invited to speak at this conference, and I'm looking forward to your reflections on what I'll be saying. I've been working on precision agriculture since the beginning of my career, which is about 30 years, and recently I've started working a little bit more on what is known as precision conservation, and that's what I'd like to talk about today. I'd like to acknowledge the funding that I've received for my research over the years. The LCCMR ENRTF funded quite a bit of the research I'll show you today. The Minnesota Department of Agriculture also funded quite a bit, and the MPCA is funding quite a few of my projects as well. So to start out, everybody knows about the Clean Water Legacy Act, which the taxpayers of Minnesota passed, and this provides funding for restoration, enhancement, and protection of impaired waters. And what we need is really to see that this money is being spent on the most critical landscapes so we get the biggest bang for the buck. And in order to do that, we need tools to identify the critical landscapes that lead to surface water quality degradation so that we can target the implementation of BMPs on the landscape. If you look at Minnesota, it has a number of water quality impairments spread throughout the state. Lakes and rivers, we have 93,000 miles of rivers, we have 13,000 lakes bigger than 10 acres. We have a lot of different types of impairments, as everybody knows. We have mercury, which is a big slice. We have dissolved oxygen, biology, bacteria, pesticides, and toxic chemicals. The ones that I tend to focus my career mostly on would be turbidity and excess nutrients, which leads to eutrophication. If you look at maps of our water quality across the state, you'll see that there are impaired lakes spread throughout the state. The red colors are the most heavily impaired lakes. The blue are the best. This map was created by Marv Bauer at the University of Minnesota using remote sensing technology. And if you go to their website, you can actually look at the turbidity or the water clarity for any lake in the state. And you can look at how the water quality changes over time. We also have impaired rivers, and the major problem in rivers is either turbidity or total phosphorus. This map shows the redder dots have total phosphorus concentrations greater than 300 parts per million. The yellow would be less than 50, and you can see that there's widespread problems. The MPCA is leading an effort to develop a total maximum daily load for Lake Pepin. This is the biggest total maximum daily load ever undertaken in the state of Minnesota. And 40% of the water from Minnesota funnels down into Lake Pepin. And the watersheds and landscapes upstream of Lake Pepin are very diverse, ranging from watersheds that are 75% agriculture to watersheds that are only maybe 10% agriculture. We also have urban watersheds as well. So precision conservation is the tool that I think we're trying to develop to get a bigger bang for the buck in terms of spending money on conservation practices. This allows small portions of the landscape that have a disproportionately high impact on water quality to be targeted with best management practices. And if we put these best management practices in these critical landscapes, we can treat small areas that have a big effect on water quality. The trick is how we identify those critical areas, and in my research, we've been using high-resolution digital elevation models from LiDAR and remote sensing. We also, of course, need information on management practices. So here is a kind of graphic that helps describe the differences between precision agriculture on the right and precision conservation on the left. I started working on precision agriculture in 1984, So I was one of the first 3 people in the world to do any kind of precision agriculture. And what we started out being interested in was how to apply fertilizer at the right place and the right time in the right amount, rather than a uniform amount across the entire field. And to do that, we would take yield maps, soil maps, elevation maps, remote sensing. We would combine them, use a GIS, use a GPS, and we would make recommendations of different kinds of, nutrients, and then go out and variably apply the fertilizer across the fields. Well, the main focus of this is to, improve the efficiency of production. There happen to be some advantages for the environment as well, because we're not over applying fertilizer. But we're really not looking at the entire ecosystem when we do precision agriculture. When we look at precision conservation, we're trying to evaluate what's not only good for the production, but also how can we optimize the environmental benefits of whatever we're doing. And we're not talking just about fertilizer, we're talking about any practice or any best management practice that could be installed to reduce sediment, phosphorus, bacteria, keep habitat in good shape. And so we look at the entire ecosystem and try to target the ecosystem to see where are the biggest sources of degradation, where are the most important areas for habitat protection, and then we try to focus our implementation of best management practices in those areas. Here's an example of some early research that was done in Pennsylvania leading to the idea of precision conservation. People in Pennsylvania started looking at landscapes that were agricultural, and they started looking at erosion potentials of the landscape as well as phosphorus concentrations in the soil. So the colors here indicate where you have a combination of factors, whether it's slope steepness or proximity to streams or high phosphorus concentration in the soils, that would lead to big impacts on water quality. And you can see that there's very small areas of the landscape that contribute disproportionately high amounts of phosphorus to surface water. So if you target just these red areas, you would have a much bigger impact than doing uniform BMPs across the whole area. In Minnesota, with research that we did from the U.S. Department of Agriculture, Adam Burr and I looked at several small watersheds to evaluate the phosphorus losses as a function of the percent of the load that they contributed. And we found that 17% of the area in one small watershed in Nicollet County contributed 40% of the phosphorus losses to surface water. So by targeting just these areas, we could reduce the phosphorus load significantly. What we're really ultimately aiming to do with precision conservation is what's illustrated on this map. We want to be able to optimize watershed functions. We want to be able to optimize the crop productivity, which would be these kind of tan colors. All of these would be kind of in, agricultural practices with conservation. And then some areas have marginal land where it really doesn't make sense economically or, productivity-wise to grow crops. So we might want to put perennial vegetation or restore habitat. We also can plant riparian areas that might also be fairly low in terms of productivity, and we can get synergy between, the perennial vegetation that's already there and new plantings to optimize and enhance wildlife. We can put in wetlands in different areas which are suitable for wetland restoration. We can plant perennial vegetation around those to provide habitat for ducks and wildlife. We can filter out sediment and phosphorus and prevent it from getting into the ditches. So if we can really think about watersheds in terms of multiple functions and try to optimize all the functions, whether it's productivity, water quality, carbon sequestration, habitat, I think then it allows us to really get a watershed that truly is multifunctional in nature and does what precision conservation is intended to do, which is, find the small areas which give you the biggest bang for your money. What we need in order to do that is to identify critical source areas. And a lot of research suggests that small areas of the landscape produce disproportionately large amounts of runoff, erosion, or phosphorus. And if we want to reduce those impacts, we need to implement BMPs in critical areas. So our approach is to define these critical areas using terrain analysis based on LiDAR digital elevation models. And we've done a lot of work with the Minnesota Department of Agriculture relating to this. We've also had funding from LCCMR and ENRTF. So the basic idea is that if you look at a landscape, you have certain areas where flow converges and certain areas where flow diverges. And in general, the areas where flow converges are the areas where you have your big, disproportionately high sediment phosphorus losses. Here's an example of a critical area that happens to be in an urban area. You can see the tremendous concentrated flow that has created off-site and on-site impacts. So other examples could be upland depressions, riparian areas, open culverts, tile outlets, gullies, ravines, eroding stream banks, and slumping stream bluffs. All of these are things we need to target. We need to find them and then go after them. So LiDAR, light detection and ranging, offers us the ability to look at landscapes in great detail. And Minnesota is fortunate in that our legislature funded LiDAR acquisition for the entire state. And we now have about 40 counties or so of data for LiDAR. You can build digital elevation models for LiDAR data. You can show contour lines, you can show hill slopes and hill shades, and you can calculate how runoff moves on the landscape and where water accumulates. This is a map showing the current status of LiDAR in Minnesota. There's a map of this in your packet. So the green is all available publicly. You can get this through the DNR website. And so this offers a great amount of information that we can use to find critical areas. With LiDAR, you can see details on the landscape that were never possible to see. If you had the standard U.S. Geological Survey 30-meter or 90-foot grids, it looks kind of blurry. You can't really see the details of the channel. You can't see the, fine nuances of how the elevation rises and falls like you do in LiDAR. Here's another example in the Blue Earth watershed, Blue Earth County, where we're working in the Buford watershed. And if you look at the 30-meter digital elevation model for this watershed, you can't really see where the ditch is or where the highs and the lows on the elevation are. With LiDAR, you can see tremendous detail. You can even see where farmers have installed terraces on the landscape. You can see the ditches, the ditch berms. You can see that the water might maybe come up to the ditch berm and then not flow over it, and it might go down slope until it finds a low spot. And so there's a lot of information here. Here's another example focused more on channels. If you look at channels or ravines with the 30-meter data, it's hard to see the details, but you really see the fine detail when you go to the LiDAR data. Here's an ortho photo, a normal orthoquad photo of an agricultural landscape near Amboy. You don't see a lot of detail on this, but when you go to the same area and you look at LiDAR, you see a tremendous amount of information. Where are the depressions that might have been, wetlands in the past? Where do you have high erosion or runoff? How would water flow? When it gets to this, it would flow, in a different direction. It wouldn't flow towards this low spot over here. So how we actually process LiDAR data, we use GIS tools, and the most latest version of Esri's ArcGIS is the tool we use. There's also a terrain analysis tool called TAU-DEM, which was written by a person at Utah State University named Dr. Tarboton. This program and others would allow you to calculate attributes, both primary and secondary attributes of the terrain, and get an idea of how water is routed across the landscape. You can combine digital elevation models with other layers such as remote sensing data, soils data, land use, land cover, and you can start to analyze landscapes to identify which ones are the most critical. Let's go into some details on how you extract attributes from digital elevation models. The most common attribute, a primary attribute, is slope steepness. Here's an example of how you divide a landscape up according to slope steepness. Now, steepness is important because it affects erosion and runoff. And so the steeper slopes would be areas where you might expect more erosion. More important, perhaps, is specific catchment area. This tells you how much water flows to any given cell on the landscape. And the higher the specific catchment numbers, the greater the amount of water that flows to those areas. So this shows that there's a channel on the landscape where the water is flowing and accumulating. We've actually calculated primary attributes for the entire state using 30-meter digital elevation models. This is the percent slope. You can see some areas that are very steep and some areas that are very flat. That translates into differences in the potential for soil erosion across the state. So you can see which areas have high and which areas have low potential erosion. And we can drill down to very fine detail. This is just a statewide map. Next, we want to look at how water accumulates on the landscape. So we use a compound topographic index, which is the specific catchment area divided by slope. So it's this map divided by this map. And the higher CTI values indicate areas where water ponds on the landscape. So these would be soils that are wet, that are perhaps ponded during the year, where you might want to restore wetlands. We've also calculated CTI values for the entire state. And so you can see that some areas are very, very high. These are the areas where water really tends to pond and accumulate, and other areas where it doesn't. It tends to run off. The third one is the stream power index. This is one we use a lot. And this is the specific catchment area times the slope. And the higher values of SPI indicate where you have a high potential for runoff. So this is where you want to really perhaps focus in on putting riparian buffer strips or looking for gullies or grassed waterways. So we've actually done an analysis of the whole state using stream power. And again, some of the areas that are steep tend to have high stream powers. You can see that here. So this is an indication of the erosive power of the overland flow. So let's look at all of this in the context of what a critical area is. Here's a photograph from, I think, Kevin Keener in 7 Mile Creek showing an agricultural landscape. You might notice this little feature here along the ditch. You see a side inlet. Critical areas have to meet two criteria. They have to accumulate surface flows, and they have to be hydrologically connected to surface waters. And this particular feature here is a side inlet, or a culvert through a ditch berm, and it collects water from this upslope area. We have another little feature down here, which you probably didn't notice. But with LiDAR, we can pick out those features very easily and very quickly. And we do that mainly with the stream power index. With the stream power index, we can identify the highest stream power values on the landscape. We can then look at any parcel of land. For example, this parcel, this field boundary, has very low SPI values. So really there's not a lot of runoff. In contrast, if we look at this land parcel, over 80% of the area is covered by high SPI signatures, meaning that that parcel of land is going to be very critical. It's going to have a big, big amount of runoff and erosivity. If you look at the ability of LiDAR to detect these stream power signatures, you see here's the 30-meter stream power signatures, and here for the same area is the LiDAR-based stream power signatures. And with the LiDAR-based stream power signatures, you see very, very high level of detail on where water is flowing, where the water intersects the ditches, and anytime you get an intersection between a high stream power signature and a ditch, that's a very good indication that you have some kind of feature there, whether it's a culvert, a gully, a ravine, or some other feature that's probably leading to water quality degradation. So you probably want to go out and look at that site and see if you need to correct whatever is happening there. With the 30-meter DEMs, we just simply don't see that level of detail. We don't even see these stream power signatures connecting to the ditch, you know, if you compare these two. Okay, so and we've done some validation in the field to see if this technique really works. We went out into, I think it was 5 different watersheds, and we randomly selected points from those watersheds to see if there were actually culverts, side inlets, gullies, or whatever. And we compared our predictions with our field observations, and we were able to predict 85% of the actual side inlets, gullies, and tile inlets. We published this in a special issue of the Journal of Soil and Water Conservation. The reference is here. So here are the research results with our random point results. Let's look at just the flow accumulation, just because it's on top here and easier to see. And then compare it with the field sampled gully and side inlets. The flow accumulation values for actual gullies were much higher than the flow accumulation values for the random points. And so we have a really strong ability then to discriminate between sites that are critical areas and sites that are not, just using flow accumulation. The same thing is even more true when we use stream power index values. There's a bigger separation between these two. So if we look at stream power index values, for example, here is some data from 7 Mile Creek. We have a stream power index signature, and where that intersects the ditch or the stream, we would predict that would be the location of a gully or an inlet. And it turns out that if we have an accuracy of 85% in terms of locating these critical areas. We've done this in the Buford watershed as well. These are all the sites that we located. Some of these are gullies or side intakes. Some are open intakes. Some are gullies. And we don't know from our GIS analysis which is which, but we know that they're important features, and when you go out into the field, you can identify which one is a gully, which one is a side inlet, which one is an open intake. You can do even more. You can analyze the catchment that contributes to each of those spots. So for each spot, there's an upslope contributing area. So for example, here's a fairly large upslope contributing area for this point here. And we can identify how big those areas are, and we can start prioritizing the critical areas according to size. You might say, well, this one's big, this one's big. Those are the first ones we want to treat. We don't want to really look at these really small ones. If we take and look at this big one, here we can see the stream power signatures and how the water is flowing. If we go out into the field, we see that it actually is a feature that needs some kind of additional work. We've got a lot of delivery of sediment and phosphorus through this particular feature to the ditch. So this is a very cost-effective way of identifying critical areas. In 7 Mile Creek, Kevin Keener, who's now with the Minnesota Department of Ag, estimated that a walking survey took 10 days and about 300 hours with 3 people. And there were costs for equipment, labor, so it was about $413 per ditch mile, and it would take 10 to 12 years to conduct the same survey for all of Nicollet County. That would cost $100,000 to $120,000. If you were to do the same kind of analysis with GIS, terrain-based analysis of LiDAR, you could do it in a matter of 1 or 2 days, and you could do the whole county. So this is a tremendous advance and a tremendous cost saving. We've done similar types of things in Le Sueur watershed, which is known to contribute high amounts of sediment, phosphorus, and nitrate to the Minnesota River. Here we've looked at riparian critical areas using the stream power index. Our critical threshold was a stream power index of 10. And we mapped critical areas for the entire watershed. They cover about 25%. And if you were to treat these areas, especially the higher areas, you could have a significant impact on upland sediment sources. Of course, there are non-upland sediment sources also. There's eroding stream banks, there's bluffs, and these actually contribute more sediment than the upland areas. But with the high-resolution orthoquad photos that come along with the LiDAR data, you can see these features. Look at that huge slumping bluff that's, eating into adjacent land. So you can actually take a virtual canoe trip down these rivers with these orthoquad photos, and you can pinpoint, yeah, that's one, that's another one, here's a third one. You can see them all. And we can map them, and that's what we've done in the Le Sueur. There's over 500 of these sites in the Le Sueur River. We know where every one of them is and how big they are. You can do the same with ravines. Here's a ravine that we've studied with funding from the MPCA. If you look at ravines using 30-meter data, it's kind of blurry. But if you go to LiDAR data, you see a huge, huge improvement. We've actually developed ways of estimating where ravines are using an algorithm that processes LiDAR data. And so we can characterize the locations, the shape, the areas, the size, the magnitude, the slope, and the gradient of all the ravines in the Minnesota River. And we have a map of that. Now, most recently, we're working on a project with funding from LCCMR, ENRTF, to identify where we can restore wetlands on the landscape. We've worked so far in 3 small watersheds. We've developed a logistic regression model based on some work that Steve Kloiber at DNR did. And this regression model tells us the probability that a point on the landscape is an upland. We can calculate the probability based on the compound topographic index, the percent of hydric soils, the slope, the curvature, and the plan curvature as well. Now, when we predict the locations of wetlands in these 3 targeted watersheds and then compare the results with either results of the renewable wetland inventory or the national wetland inventory, we get a very high accuracy, anywhere from 70 to 90% prediction accuracy. So the blue colors are the predicted wetland locations based on our probability approach. The red outlines are the locations of wetlands from the NWI, the RWI, and pre-settlement data that's available in 7 Mile Creek watershed. So we have a very high ability to predict where wetlands are located. We've completed a project for the Environment and Natural Resources Trust Fund called Statewide Ecological Benefits Index. We worked in partnership with the Board of Water and Soil Resources. And the objective of this was to more effectively target conservation programs to CRP lands and other critical lands, such as marginally productive lands, areas that need surface water protection, and important habitat areas. Basic idea behind this tool is to take digital layers for soil erosion, terrain analysis, surface water proximity, habitat, and translate those into soil erosion risk, water quality risk, habitat quality, and assign a certain number of points to each of these, add the points up, and get an environmental benefits index. The higher the environmental benefits index, the more important that parcel of land is for conservation efforts. That would be our final priority ranking. So the high EBI means a high risk of water erosion or runoff, a high quality of habitat, and a high value of conservation. We've created maps for the entire state of Minnesota on 30-meter parcels, so you can look at any 30-meter parcel in the entire state of Minnesota, and you can get its environmental benefits index score. what you would see in this map, for example, is that there's a lot of high EBI scores around these lakes, and that, in my opinion, would be where you'd want to start in terms of installing conservation practices. Here's a more detailed view of a similar map showing, you know, the high EBI score areas around lakes. Now, the Board of Water and Soil Resources is taking this tool and using it for a new program called the Rim Buffer Program. They've expanded the geographic scope of the old RIM program, which was initially focused mostly in the Minnesota River, and they've accepted applications from regions that are highlighted here in this yellowish green color. All the little watersheds here are watersheds that are have been approved for you know, easements in the riparian rim buffer program. So the tool that we've developed is now mandatory for people who want to apply to this program. They go to this website at Bowser. They can get an interactive map showing the EBI scores for any parcel of land in the state of Minnesota. They can then scroll down to their watershed and look at the average environmental benefits index score for their watershed. Every watershed is mapped out, and you can find the environmental benefits index and then use that interactive tool to identify the high priority project areas in your county. And then that gives you an advantage when it comes to applying for this money, because if you target the highest EBI score watersheds, you get a higher score in terms of the ranking on the proposal. We're also working with the Minnesota Department of Agriculture to identify priority management zones in watersheds in Washington, Chisago, and Stearns County. This happens to be a map of one of the watersheds we're working in Stearns County. So Dennis Fuchs told us which watershed he thought was a high priority, and then we went in with our environmental benefit index score. So the redder colors are higher EBI scores. And then we used LiDAR data for this particular watershed to identify stream power signatures, where they intersect with the streams, and we've identified all the potential areas which we think are critical source areas. We've also found a few ravines that we think probably should be looked at. So we've done this also in Washington County, a very different landscape, and you can see again the critical areas and the stream power signatures in yellow. What we're ultimately trying to get to perhaps is linking these LiDAR-based tools with process-based simulation tools. A lot of you are familiar with using Russell II and the Soil Water Assessment Tool, or SWAT, to estimate erosion and phosphorus losses from landscapes. Well, we can combine the LiDAR-based tools with those mechanistic models to improve the performance of those mechanistic models and allow them to incorporate these critical areas. And this map is a little bit complicated, but I want to show you what we're doing with this particular project. This project is funded by MPCA, and what the intent is to look at 3 watersheds, including 7 Mile Creek, which is here, to find out where we get the greatest ecosystem services from installing conservation practices. Ecosystem services are things like water quality, carbon sequestration, habitat, and of course, production of food and fiber. What our approach is to use the Soil Water Assessment Tool model combined with the LiDAR-based terrain analysis tools, identify critical areas, and then simulate the effects of different alternative practices in various parts of the watershed. The baseline land use is shown up here. This is mostly all in conventional agriculture. That would be the brown color. There's a few areas with grass. There's a few wetlands. Now, if we start looking at what is the optimum landscape for different amounts of reduction in phosphorus loss from the watershed, so here, if we wanted to say get a 30% reduction in phosphorus, we would go to scenario B, which is this scenario. That would be the most optimum scenario. It involves conservation tillage in some areas, conventional tillage in some areas. We have a little bit of perennial grasses. And it doesn't cost very much to do that. The cost is less than maybe $100,000 to get to 30% reduction if we target our practices in an optimal way. If we want to go to a 50% reduction, we have to go to this landscape. So now we have more areas that are in conservation practices. We have more areas in grass. If we want to go to even higher levels of performance, we have to take a lot of row crop and put it into grassland. If we want to get 80% reduction, then the whole watershed needs to go to switchgrass. So, I mean, this just shows you, and it would cost about $2.5 million to make that switch. Now, in comparison with this, what happens with our kind of conventional approaches to conservation if we don't use targeting? For example, what if we just put, grass buffers around all the ditches? Well, that particular scenario, G, would only give us about an 18% reduction. It would not be very optimum. What if we treated only the high erosion areas? That would be this option right here. So you can see that with these tools, we have the ability then to really try to optimize the function and the performance of our BMPs across the landscape. So to conclude, conservation practice implementation is neither economically nor environmentally efficient when done uniformly across the landscape. Disproportionately small areas contribute disproportionately large amounts of sediment and phosphorus. The effectiveness of the BMPs depends on placing them in vulnerable portions of the landscape. Precision conservation strategies involving LiDAR-based DEM or terrain analysis may prove to be very useful in the future to help guide conservation efforts tailored to specific landscapes so that we can get the biggest bang for the buck in these critical areas. Tools for analyzing LiDAR-based digital elevation models need to be developed and integrated with existing conservation planning tools such as the Minnesota Phosphorus Index, Russell II, and SWOT. That concludes my presentation. Thank you very much. I'd also like to acknowledge the people listed down here who collaborated with me and did a lot of the work that's shown here.
We have time for a few questions that Dr. Mulla can take from the floor.
I've got a question on subsurface drainage. We see a lot of tile going in some of these areas now. They don't always follow watershed boundaries. How does that affect some of your models?
Right. Okay, so the question was, how does the presence of subsurface drainage affect our models? I actually am working on that right now with this LCCMR project that deals with wetlands. And what we're doing is trying to actually intersect the wetland probabilities with tile drainage maps. Rick Moore, who might be here, has digitized subsurface tile drainage networks for a large part of the Minnesota River Basin, and he's shared some of that with us. We're intersecting those subsurface tile drainage maps with the wetland probability maps to see where we might really be able to get the best potential for wetland restoration. We'd like to have tile drains that flow naturally into a depression, which could be a restorable wetland. With the stream power signatures, we found that the presence of side inlets that really discharge the subsurface tile outlets or subsurface tile flow into a ditch, we can identify where those side inlets are with our LiDAR-based terrain analysis, because the side inlets tend to be in the low spots on the landscape. So that's a twofold or two-part way of answering your question, is that one, we are trying to incorporate tile drainage into our wetland restoration work, and number two, it seems that the outlet points for those subsurface tile drains do correspond very closely with our stream power signatures.
Beth, you had a question? You said
Okay, the statewide terrain analysis maps are a part of the Environmental Benefits Index. So if you go to the website and you see this interactive map, it's got a little button down at the bottom which says download data layers. So you can go there and you can download the individual data layers that went into making this. That was the intent, is so that local units of government could play with the data and do things that we had never envisioned. You know, we can't think of every, perhaps, application, but people out in the watersheds, in the SWCDs, non-governmental organizations, they're very creative. And we hope that you'll make full use of all these products.
Dr. Mulla, you have to repeat this about how to run it. But have you quantified, say we have 2 acres, one is one of your high priorities, one is a low priority, that this is 5 times more impact than this, 10 times impact?
So the question was, if we have 2 parcels adjacent to each other, one has a high environmental benefits index score and one has a lower EBI, have we quantified the relative, you know, differences in terms of, say, soil erosion or phosphorus loss? We haven't actually tried to do a quantitative prediction of the amount of soil loss from an individual parcel or the phosphorus loss, because that requires having management data for that parcel. We need to know whether there's a corn soybean rotation, a corn alfalfa rotation, whether there's conservation tillage. Some of that type of data is not available to us when we do this large-scale analysis. But we're hopeful that people, again, at the local level who have access to that data could incorporate it into our evaluations and start doing more of those quantitative comparisons.
In the back.
Dr. Mulla, your talk has been primarily about surface water. Can the tools that you're developing be used for identifying critical areas for recharge for groundwater in the state?
Did everybody hear that? Okay, can our tool be used to identify critical areas for groundwater recharge? We haven't looked at that yet, but we did notice when we were working with this tool in southeastern Minnesota that it was very clear the terrain attributes are closely linked with the presence or absence of sinkholes. So in that particular case, I think we will probably be working next on developing a tool that can evaluate the location of sinkholes. So it's not really exactly what you were asking, but we're kind of moving in that direction.
Any other questions for Dr. Mulla?
Very nice presentation. This is a naive question in some sense. Farm production machinery seems to have grown in size and sort of needing large scale, they do uniform production practices on landscapes. This calls for more targeted conservation, but it also seems to suggest more targeted cultivation. How does this idea flow into the production community?
So the question was about how the large size of farm equipment would perhaps be compatible with the things that we're developing here in terms of being specific to these conservation areas. Yeah, well, there are a couple of issues here. One is that farmers have these large, you know, tractors and combines, and it's hard to move around small areas, and they prefer to drive in straight lines. However, one of the biggest new technologies in farming community today is auto steer. And farmers are buying these high precision GPS systems, installing them on their tractors and their farm equipment, and using the equipment to actually drive the combine or the planter for them in very precise paths that are pre-programmed. So potentially that technology could be used to, you know, help drive around some of these critical areas and make it easier for the farmer to program that in. With this new technology, you can guide the tractors along paths that are accurate to a level of 1 or 2 centimeters, maybe an inch or so. So it's really impressive. And it saves a lot in terms of time for the farmer. It reduces their fatigue and allows them to do things that they haven't been able to do in the past. I think my time is up. Thank you very much and have a good day.